Okay, Chapter 3, Section 5, Implicit Differentiation. Okay, so in this section, we're going to learn a new technique for taking derivatives. So let's start with the following example. Okay, so given 2x cubed minus y plus 3x equals to 7, find y prime. Remember that we have a lot of different ways in which we can represent a derivative. This is one of them, y prime. Also, we could say dy dx, right? Or dy dx, same thing. All right, well, if we want to find the derivative based on what we know so far, it seems logical that the first thing we'd want to do is solve for y. So first, solve for y as a function of x. Right? So in other words, get the y by itself on one side, and on the other side, all the x's. Right? Thus, the x is the independent variable, and the y is the dependent variable. This one's very easy to do that. Okay, and once we've done that, then we'll take the derivative. With respect to x. Okay, so let's apply those two rules here. Okay, so step one, let's solve for y. Very easy here. We got 2x cubed minus y plus 3x equals to 7. Let's add y to both sides. Plus y plus y. And then I'm going to subtract 7 from both sides. Minus 7 minus 7. So all of that comes down here to 2x cubed plus 3x minus 7 equals to y. And then I'm just going to rotate, flip that over, and I get y equals to 2x cubed plus 3x minus 7. So step one complete. Okay, so now I'm ready to take the derivative. So then y prime is equal to the derivative with respect to x of this function, 2x cubed plus 3x minus 7. And so y prime is going to be equal to ddx of 2x cubed plus ddx of 3x minus ddx of 7. Okay, so y prime is equal to 6x squared plus 3. Right, the derivative of 3x is just going to be 3, and the derivative of 7 is going to be 0. Right, so let me make sure that's clear. The derivative of this is just the 3, and the derivative of this is 0. So there we go, there's my answer. Easy, no problem. Okay, so we were originally given this equation up here, and we want to find the derivative of dy dx, or y prime. And so step one is to solve for y, and then take the derivative. What we want to do in this section is develop the idea that we can skip this first step. We can find the derivative without solving for y. Just go right for it in the following way. So we have 2x cubed minus y plus 3x equals to 7. Okay, we're going to take the derivative. Now we have to know what the variable of differentiation is. We have to know that this is with respect to x. Okay, so when you're asked to find dy dx, you have to pay attention to the fact that the derivative of differentiation is the x, dy dx. Okay, so we're going to take dy dx of all of this, minus y plus 3x, even the other side, the whole thing, the derivative of the entire thing. Okay, so now let's separate these guys. This means that this is going to be d dx of 2x cubed minus d dx of the y plus d dx of the 3x equals to derivative with respect to x of the 7. Okay, well, a couple of these derivatives are super easy. Just like before, nothing has changed. Here we have a function in x, and we want the derivative with respect to x, so we just take this derivative. This is just going to be equal to the 6x to the power of 2 that we got before. Minus, okay, I'm going to skip that for a second. So blank there. Plus, okay, now this derivative is super easy as well. We have a little equation, a variable x, and we want the derivative with respect to x, so this is just going to be the derivative of this, which just equals to 3. Equals. And now the derivative with respect to x of a constant 7, well, that's just going to be 0. Okay, now what about this guy? What is this? Well, this is dy dx. This is in fact exactly what we're looking for, right? Remember that the notation in derivatives can vary. So coming back up here, we can say y prime, or we can say dy dx, or we could say d dx of y, right? They all mean the same thing. So that's what this is. This is dy dx. It's what I'm after. It's the derivative with respect to x of the y function. Okay? Now, we can write this down because we are assuming that it exists. Now, I know that it exists. It's over here. I found it already, right? But I'm kind of cheating because I already knew the answer by doing it this way, and now I'm coming back over here and I'm doing it a different way. So I already know this exists. But that might not be the case. There might be some function out there where the derivative doesn't exist. So then you're writing something down and it's like, oh, well, that doesn't even exist, right? So we write this down and we kind of imply that it exists, right? That's why it's called implicit differentiation, because we're kind of crossing our fingers and going, well, okay, as long as this exists, well, there it is. That's what we're after. Okay? All right, and note that once we have this, well, this notation is awkward, but it's the derivative, right? So we can just go back to this notation, y prime plus 3 equals 0. And now all we have to do is solve for y prime. Okay, so y prime, I'm going to add y prime to both sides, like any other variable, solve for y prime. So plus y prime plus y prime. And we end up with 6x squared plus 3, right, these guys cancel, equals y prime on the other side. And then if I just flip it around, I get exactly the same answer as before. Y prime equals to 6x squared plus 3. Same answer as before. Okay, so what is the point here? The point is that we didn't have to solve for y if we do it this way. Put or. This is called implicit differentiation on this side. Put or. And over here, this is implicit. Okay, so that's the big advantage here. We don't have to solve for y first. We can just start taking derivatives without solving for y first. And when you run into the derivative of something with respect to x, keeping in mind that x is the variable of differentiation here, when you run into that, you just take the derivative like normal. Like here, the derivative with respect to x of this one, no problem, just like before. The derivative with respect of this one and this one, no problem, just like before. It's really when you run into the y that looks a little bit weird. And just remember that the derivative with respect to x of the y, that's exactly what we're after. Okay? All right, so in this particular example, the advantage is not super clear. Hopefully you see that I can get the same answer in both ways. In this particular example, you know, maybe it's not super clear why we would care about implicit differentiation. But let's do an example next where hopefully that'll be clear, because the advantage comes in that sometimes these equations are really hard to solve for y. So this first step might take you for a long time. And the result might be really, really ugly. It might be very hard to find that derivative once you finally solve for y, or there might not be a solution for y. That might not be possible to solve for y. So you might not be able to do it in this way. Okay, so if you can do it this way, great. It's probably the easiest, best way to do it. Solve for y. If it's quick and easy like this one, then take the derivative, no problem. But in many cases, it's difficult or impossible to solve for y, so we have to use implicit differentiation. Okay, let's look at another example. Okay, consider this one now. X cubed plus y cubed equals 6xy. It's really, really difficult to solve for y, right? To get the y by itself. We can't just move the x cubed on the other side, because then we'd have a minus 6xy, and it's just hard, right? So it's really difficult. It is possible in this case, but it's really, really difficult, way beyond the scope of our class to be able to figure out how to do it. But we can find y prime. So, comma, find y prime. Note that y prime then by default must mean that the other variable is the independent variable, right? This means dy dx. Same thing, right? And this is the same thing as d dx of the y. Same thing, right? All of them mean the same thing. Okay, so let's find y prime. So let's just start taking derivatives. Derivative with respect to x, because I'm looking for y prime, of everything. So this would be x cubed plus y cubed equals to 6xy. Good. Now let's take derivatives. So it'll be the derivative with respect to x of x cubed plus the derivative with respect to x of y cubed equals the derivative with respect to x of 6xy. Okay, this one's easy, no problem. The derivative with respect to x of x cubed, see the variables match. So this is just going to be our power rule. This is going to be 3x squared. No problems there. Okay, what about this one? Well, it's not as easy as before, where I just said, well, that's just dy dx, because of this cubed here. Right? So this is actually going to be a chain rule. We're going to pretend that we're taking the derivative with respect to y. So this is going to be equal to 3y squared times the derivative of the inside part, which is going to be the y, times d dx of the y. Good. So take the derivative with respect to y, and then times the derivative of the inside part. So this is the chain rule, and now this is what we're after, right? Dy dx. Okay, now here we're going to have a product rule. We have, well, the 6 can go away. Let's just factor out the 6. But then we have x times y, so it's a 6 times, and then the product rule says we're going to have d dx of the x times the y plus, now leave the x alone, times d dx of the y. Right? Just to make sure the parentheses are here clear. This is the derivative with respect to x of the first one, and then this one, the derivative with respect to x of the next one. Right? That's the product rule. Okay, so let's keep going. This is going to be a 3x squared plus 3y squared, and this is that dy dx, right? And this is where we're making that assumption that it exists, right? That's that implicity thing. It's implied that y can be expressed in terms of x, therefore its derivative exists, and so I can write it this way. Okay, so we're implying, or we're hoping, we're assuming that this derivative exists. Okay, so now this on this side would be 6 times. Now the derivative with respect to x of x is just 1. So this would be 1 times y plus x times, and again, that's just going to be that dy dx. dy dx. Good? Okay, very messy. I'm going to go back to the y prime notation because otherwise, to me, this looks kind of messy. But you can leave it alone if you'd like to. This is y squared times y prime equals 2. And I'm going to go ahead and distribute this 6. This will be 6y plus 6xy prime. Okay, we're almost there. But remember, our goal was to solve for y prime. And, well, we have y prime there and y prime there. So now we just have to do a little bit of algebra work to solve for y prime. Okay, so I'm going to move all the terms that don't have a y prime to the right side. So I'm going to subtract 3x squared from this side. And I'm going to subtract minus 3x squared from this side. And then I'm going to move all the terms that do have a y prime over to the left side. So I'm going to subtract 6xy prime minus 6xy prime on this side. Okay, so let's copy that. So on the left side, these guys will cancel, leaving me just 3y squared y prime minus 6xy prime is equal to 6y minus 3x squared, and then those guys cancel. Good? Okay, so now what I want to do now is factor out the y primes. I have a y prime there, I have a y prime there. I'm going to factor it out, so I'll have y prime parentheses 3y squared minus 6x equals to 6y minus 3x squared. Okay, so I'm almost done. Let me take this guy and move it over here. So we have y prime 3y squared minus 6x equals to 6y minus 3x squared. And so now I just want to divide both sides by this little binomial. So divide this side by 3y squared minus 6x. Divide that side by 3y squared minus 6x. And then here it'll cancel, become 1. And that's our final answer. Y prime times 1. So on the left-hand side, we just have y prime. On the right-hand side, we have this little division. So we have 6y minus 3x squared all over 3y squared minus 6x. And that's my final answer. When you're given a function where it's not clear, it hasn't been solved for y, it's all mixed in there, x's and y's all over the place. If it's really easy to solve for the y, go for it. Solve for the y real quick, and then you can solve or find the derivative just the way we've been finding them before. On the other hand, if it's mixed in there, it's really hard to factor it out. It's really hard to solve for the y and get it by itself. That's a place where this implicit differentiation comes in handy. Okay, so you just start taking derivatives like normal. Just take the derivative of everything. Just take the derivative of everything, and you have to be careful. You have to kind of decipher what the variable of differentiation is. Now, usually, algebra loves x's and y's, so that's what I've been sticking to so far. But normally, we like to have y as our dependent variable. Normally, y equals the dependent, and x is the independent. So y prime is dy dx, so the variable of the differentiation is the x. But that's not always the case. We could just have letters A and B, for example, or P and Q, for example, right? So it could be any letters. So you're going to have to, think for a second and figure out which one is the variable of differentiation. So we'll do an example like that in a second. But if this was written as m cubed plus b cubed equals to 6m b, and you're like, okay, well, which one's the y, which one is the x, right? The y, which one's the independent, which one's the dependent? Well, it doesn't. The clue you should look for is the question that they ask you. If they say find m prime, right? That means that the variable of differentiation is the other one, right? When they ask you to find y prime, the variable of differentiation is the x. It's the other one. If they ask you to find m prime, and this is what they gave you, then we're taking the derivative with respect to b. So as we go through, this will be a normal derivative because it's with respect to b, but we'll end up with our implicit derivatives here when we take the derivative of m cubed with respect to b. Okay, all right, we'll do an example like that next. Okay, so if we're given 3a squared plus a cubed b cubed plus 1 equals to 0, find b prime. Okay, so by the fact that they're asking you to find b prime, it must mean that the other variable is the variable of differentiation. This must be equal to dA of the b, or dB dA. Good? Okay, so let's go ahead and find it, which means we got to take the derivative with respect to a. We have 3a squared plus a cubed b cubed plus 1 equals 0, and we want to take the derivative of the entire thing with respect to a. Okay, so the first one should be nice and easy. Derivative with respect to a of 3a squared. The variables match. We have the variable of differentiation is a, and this is written in a, so that should be an easy derivative. Plus, okay, so now we're going to need the derivative of this, but it's a product rule. So it's going to be, let's put it as a little product rule here, this is going to be equal to the derivative with respect to a of the first one times b cubed, plus, now we leave the first one alone, and then the derivative with respect to a of the second one cubed. Okay, so that's a little product rule. Plus the derivative with respect to a of the 1 equals to the derivative with respect to a of the 0. Okay, so, and then just to be really clear here that this derivative only applies to the a cubed, not the b cubed. Let's just wrap it in some nice colorful brackets, and so does this one only apply that one. Okay, so now let's take these derivatives. So this is going to be a nice, easy derivative. They match. The variable of differentiation is an a. This is written in a. So this is equal to 6a to the power of 1, or just 6a, plus, and now this, again, this matches. Variable of differentiation is a, and this is written in a. So this is going to be equal to 3a squared b cubed, plus, and now we leave the a cubed alone, times, and now here's where they don't match. So we're going to assume that the derivative exists, and we're going to use our chain rule to rewrite this as 3 times b to the second power times the derivative with respect to a of the b, plus, and now this is easy, the derivative of a constant is going to be equal to 0, and the derivative of 0 is going to be 0. So this is really just plus 0 equals 0. Plus 0 equals 0. Easy. And this is really the only one, the only derivative b prime they're going to run into. So let's simplify this a little bit. We get 6a plus 3a squared b cubed plus 3a cubed b squared times, and I'm just going to rewrite it as b prime, dBdA, just b prime, equals 0. We're almost there. We just have to solve for b prime now. That was the original That was the original question. Okay, so I'm going to move these two terms to the other side, and I get 3a cubed b squared times b prime equals to minus 6a minus 3a squared b cubed. And finally, just divide both sides by 3a squared b squared, and that'll be my final answer. B prime is going to be equal to minus 6a minus 3a squared b cubed divided by 3a cubed b squared. Notice that our derivative is not quite as satisfying as in previous sections before implicit differentiation, because our derivative is now a function of both a and b. It's not just one variable. We need both the input and output pairs of our original function in order to find the value of b prime. All right, let's do another example. Okay, find the equations to the tangent lines to the equation 3 minus y plus 2xy squared minus x squared equals to 2 when x equals 1. Okay, the first thing we have to do is think about the ordered pairs that are solutions to this equation, where x equals to 1. So we need to find the other values of y such that x comma y solve this equation. Okay, so let's begin there. Let's replace x with a 1 and solve for y. So step 1, we're going to do 3 minus y plus 2 blank y squared minus blank squared equals to 2. And we're going to replace all those x values with a 1. 1, 1, since we're told x equals to 1. Okay, so let's solve for y. 3 minus y plus, that's just going to be 2y squared minus 1 equals to 2. 3 minus 1, that's going to be 2. 2 minus y plus 2y squared equals to 2. If we subtract 2 from both sides, we get a 0. Minus 2 minus 2. So we get minus y plus 2y squared equals 0. If we flip that around and factor out a y, we get y times 2y minus 1 equals to 0. Right? So if I distribute, I get 2y squared minus y, and that's what this is. The zero product rule lets me separate this. So one solution is going to be 0. Y equals to 0 is going to be one solution. And the other solution is going to be 2y minus 1 equals to 0, which means that 2y equals to 1, or that y equals to 1/2. Okay, so we have two ordered pairs that solve that equation. From here, we're going to get that one solution is going to be 1, 0. And from here, we get that another solution is going to be 1, 1/2. Right? That's, again, where the x is equal to 1, and so the y equals to 1/2. And here we get that x is the 1, and of course the y is equal to the 0. If we wanted to check these and make sure that they make sense, if we wanted to check them, we can come back to our original equation and replace all the y's and all the x's with one of the ordered pairs. So for example, here let's replace the y with a 0. That's going to be easy. That's 0. Well, y 0 squared, that's 0. This whole thing is going to be 0. So the middle two terms disappear when the y is 0. And when x is 1, we end up with 3 minus 1 squared. And yeah, that's going to be equal to 2. So clearly that's a solution. And now if we come back and replace all the y's with a 1/2, 1/2 squared times 1 times 2, and replace the y with a 1/2, and simplify the whole thing, we'll see that we also get another valid solution. Okay, so we have our two ordered pairs, but that's not what they asked us for. They want us to find the equation of the tangent lines to both of these points. So in order to find the equation of tangent lines, we need to find the derivatives at those points, right? So we need to find y prime. So let's take the derivative with respect to x of the original equation. Okay, so we're going to get the derivative with respect to x of 3. We know that's going to be a 0. The derivative with respect to x of the variable y, they don't match, so we know this is going to be the y prime. This is what we're after. Plus, and then we have a little product rule here. So let's do 2x times the derivative with respect to x of the y squared. Plus, now let's leave the 2 and the y squared alone, times the derivative with respect to x of just the x, right? So we take turns, minus the derivative with respect to x of the x squared equals the derivative with respect to x of 2. And so we know that this one's easy. That's just going to be a 0. And we know this one is just going to be a 0. So let's simplify this. That's just going to be 0. This is what we're after, so this is going to be minus y prime plus 2x, and now the derivative of this, we got to use our chain rule. It's going to be 2y times dy dx, which is going to be the y prime, plus 2y squared times, and then the derivative with respect to x of the x function, that's just going to be 1, minus, and then the derivative of this function is going to be 2x to the power of 1, or just 2x, equals, and then on the other side we just have a 0. So we're almost there. Let's get all the terms that have a y prime together, which they are here, and let's move everything that doesn't have a y prime to the other side. I'm going to flip these around as well, so this is going to be 2x times 2y. Okay, I should probably just simplify that to be a 4. So I'm multiplying these, so it'll be 4xy y prime, 4xy y prime minus y prime is equal to, now I'm going to move these two terms to the other side, so I'll make it plus 2x minus 2y squared. Good. Next, I'm going to factor out the common y prime and then divide. So we'll get y prime times 4xy minus 1 equals to 2x minus 2y prime. Good. And now we divide. So y prime ends up being equal to 2x minus 2y squared divided by 4xy minus 1. So there we go. Here is our answer for the derivative. And notice, like I pointed out a minute ago, it's an unsatisfactory kind of answer because the answer involves both the variable x and y, right? So we have to know the ordered pair in order to find the derivative. Luckily we do. So let's go back over here. Let's zoom out. Okay, so we're interested in finding the tangent line at this point and the tangent line at this point. So let's do them one at a time. I need to be able to find the derivative at this point. So actually, just to make a little bit of space, I'm going to move this over here and say from here this way, this is going to be y prime equals to 2x minus 2y squared divided by 4xy minus 1. So let's put that up in a little box over there. And that way it gives me a little bit of space here. Okay, so now for the point 1, 0, let me zoom into there. For the point 1 comma 0, then it's implied, or not implied, we know that the x is the 1 and the y is a 0. And now we can use this formula to find the slope of the line tangent at that point, the derivative. So y prime is equal to 2 times blank minus 2 times blank squared all over 4 times blank minus 1. And so the 1 is an x, so x is 1, and then the y is a 0, so 0 there, 0 there. Okay, so we just have to simplify this a little bit. We get y prime equals to, this is going to be 2 minus 0, so that's going to be 2 in the numerator, divided by, this is going to be 0. 0 times anything is 0. 0 minus 1 is negative 1. So y prime equals to negative 2. Okay, so now we have the slope of the line tangent, and we have a point, right? So now all we have to do is use our formula for lines. So now, we're going to use y minus y sub given, for some point given, m times x minus x for some point that is given. Okay, and what are those given points? Well, this one, and this is the slope, right? M is going to be equal to negative 2, where m is the slope of the line tangent. Slope of line tangent to our original equation, at point 1 comma 0. Okay, so that's what we need right here. So let's substitute everything. We get y minus 0 equals to negative 2 times x minus 1. Distributing, we get y equals to minus 2x plus 2. That's our answer. This is the equation of the line tangent to the point 1 comma 0, tangent to our original equation at the point 1 comma 0. Okay, 1 down, 1 to go. We know there's another one. We have, for the other point, 1 comma 1/2. Again, we need to figure out the derivative at that point, the derivative of the line tangent at that point. So y prime is going to be equal to 2 times blank minus 2 times blank squared, all over 4 times blank minus 1, right? Again, following our formula for the derivative. And this is where the x is a 1, so put a 1 there, put a 1 here. And the y is a 1/2, so we're going to put a 1/2 there and a 1/2 there. Okay, so let's try and simplify this. 1/2 squared is 1/4. 2 divided by 4 is equal to a half. So this is going to be y prime is equal to 2 minus 2 times 1/4. So that'll simplify a little bit there. And then 4 times a half, well, that's just 2. 2 minus 1 is just going to be 1. Y prime is equal to 2 minus 1/2 divided by 1. And 2 minus a half, that's just going to be 1.5 as a mixed number. Y prime equals to 1.5 as a mixed number. 2 minus a half is 1.5, which is the same thing as 3 over 2. Okay, so now we got our slope of the line tangent to our original equation at this point. So now let's find the equation of the line. So we're going to go back to using y minus y sub given equals to m times x minus x sub given. Except now in this case, we're going to use 3 over 2 for the slope. X minus 1 equals to y minus 1/2. Good. So solving for y, we're going to get y minus 1/2 equals to 3 over 2x minus 3 over 2. And so y equals to 3 over 2x minus 3 over 2 plus 1 over 2, which gives you minus 3 plus 1 is going to be y equals to 3 over 2x minus 1. And so that's the equation of the other line tangent. Good. Okay, let's zoom out and take a look at the whole thing. Okay, so we were given originally this equation right over here, 3 minus y plus 2xy squared minus x squared equals to 2. And we're tasked with finding the equation of the line's tangent to this equation when x equals to 1. So the first thing we have to do is evaluate this given equation when x equals to 1 and solve for y, so that we can get the ordered pair values that satisfy that equation. Okay, so we found them. One ordered pair was 0, 1. The other ordered pair was 1, 1/2. Once we have that, next we have to find the derivative of our function, because we need to figure out the slope of the line's tangent at those points. So we start taking derivatives. We use implicit differentiation. So we worked it all out, and we found out that this is the equation of the derivative. Notice that when we do implicit differentiation, we end up with an equation that requires both x and y in order to figure out that derivative, right? So we needed to do step 1 over here. Okay, oh, well, I guess this is step 2 over here. Step 2. Step 2 was to find that derivative. And then finally we got to step 3 over here. So now that we have an ordered pair and we have an equation that can give us the slope, we plug it in and find the slopes. Next we find our actual equations of our lines. Okay, let's graph this one and see what it looks like on Desmos. Okay, so this is what our graph looks like. Very interesting, weird looking function, right? We can understand why it is difficult to think of this as solving for y, right? This isn't really a function. It doesn't pass the vertical line test. But, okay, we're able to get by that anyway by using our implicit differentiation. So let's see, when x equals to 1, we got a couple of ordered pairs. We got 1, 0. Okay, 1, 0. And then the other one was also on there, was 1, and then 1/2. So there they are. Those are the 2 points on my function that I was interested in. I'm going to zoom in a little bit. There they are, this point and this point. Those are the 2 points. So I want the line's tangent to those. So we worked it all out, and for one of them, the equation was y equals to negative 2x plus 2. And for the other one, it was y equals to 3 divided by 2 x minus 1. There they are. Let me put them in red and red, and I guess I'll put the points in green. Green and green. Okay, so there they are. Those are my 2 equations that are tangent at the points. Okay, so let's label some stuff then. Everything in blue, all of it, is our original equation. So this thing here is 3 minus y plus 2xy squared minus x squared equals to 2. So both this one as well as that one, right? All of the blue, all blue, is our original equation. Okay, we were asked to figure out the equations of the line tangent when x equals to 1, and then we figured out that there were two places where x equals to 1. There was this point right there, so that's the point 1 comma 0. And then there was also this point right there, which was the point 1 comma 1/2. Good. And then after doing a bunch of work, we figure out the tangent lines at those points. So the tangent line at 1 comma 0, that's this equation. And at 1 comma 0, we got that it was the equation y equals to negative 2x plus 2. From here, clearly we can tell that the slope m equals to negative 2. It's got a negative 2 slope, and the y-intercept goes through the point 0 comma 2. Y-intercept at 0 comma 2. And we can see that indeed it does cross the y-axis right there at 0 comma 2. Okay. The other equation was this one, and so this one right here is the tangent line to the point 1 comma 1/2, and we found that its equation is y equals to 3 divided by 2x minus 1. That's this equation. And from here, of course, we can tell that the slope of that line is m equals to positive 3 divided by 2, and that it goes through the y-intercept at 0 comma negative 1. Good. At 0 comma negative 1. Okay, so we got everything we needed. All right, now let's work with this one. Say cosine x plus y equals y squared of sine of x, find y prime. Okay, so we're going to take the derivative with respect to x, since they're asking us for y prime. So we're going to do d dx of everything. So it'll be cosine of x plus y equals to y squared sine of x. Okay, so let's take derivatives of each one of these. So then it'll be the derivative with respect to x of cosine x plus y equals the derivative with respect to x of the y squared sine x. Okay, so the derivative of cosine is going to be negative sine, so this would be negative sine of x plus y times the derivative of the inside part, so times d dx of the x plus y equals, and now here we have ourselves a little product rule. So it'll be the derivative with respect to x of y squared times sine x plus y squared times d dx of sine x. Good, so we have a little product rule we got to deal with there. Okay, so here we end up with negative sine x plus y times, and now the derivative of x is just going to be 1, and so we'll end up with 1 plus the derivative with respect to x of y. That is exactly what we're after, so I'll just put it as a y prime, right? You could also write dy dx if you want to. And this equals, okay, so now the derivative of this guy using our chain rule will be 2y times y prime sine of x plus y squared times, and the derivative of sine x is equal to cosine x. Cosine x. Good. Okay, so now remember, we're trying to isolate the y prime. That's what we wanted to solve for. So let's distribute this negative sine of x plus y. and then move all the terms with a y prime to one side, all the terms that don't have a y prime to the other side. So negative sine x plus y minus sine x plus y, y prime, equals to 2y, y prime, sine x plus y squared cosine of x. Good. So now I'm just going to move this term because it has a y prime to the left-hand side, and this term to the right-hand side. So we're going to do a plus sine x plus y, add that to this side, plus sine of x plus y, and then I'm going to subtract minus 2y, y prime, sine of x from this side, minus 2y, y prime, sine of x on the left side. Okay, so let me include that. All right, so some stuff will cancel. These eliminate, those guys reduce, these guys reduce. So we'll be left with minus sine x plus y, y prime, minus 2y, y prime, sine of x, equals to y squared cosine of x plus sine of x plus y. Good. Okay, so now we factor the y prime. We factor the y prime, and we get y prime times negative sine x plus y minus 2y sine of x equals this, y squared cosine of x plus sine of x plus y. Okay, so finally, all we have to do is divide both sides by this binomial, and that'll solve for y prime. So divide this left-hand side by negative sine x plus y minus 2y sine of x, and divide the right-hand side by minus sine x plus y minus 2y sine of x, and that'll get us to our answer. So let me zoom out a little bit. And so our answer is right here. Okay, so there's our answer. Okay, so we definitely know the derivative of sine. So we definitely know that the derivative of sine x is cosine x. But what about sine inverse? Derivative with respect to x of sine inverse. What is that? Okay, so in order to answer this question, let's go back and review what sine inverse even means. And then we'll use implicit differentiation to be able to figure out what this is. Okay, so let's go back to our standard graph of the sine function. So in a sort of standard form of the sine function, we like to use y equals to sine of x. Here, note that the input here, the input is an angle. Input an angle. And an output value is a value, a decimal between -1 to 1. Okay, but what about if we want to go backwards, right? So if we have some value a and we map it up to there, this maps out to some decimal value there, which gives you some value, say b, maps out to b. So this ordered pair right here is indicating that sine of a equals to b. So normally we start off with an angle. We input an angle to the sine function and we get some sort of output. But what if we want to go backwards? What if I want to give you the value b and I want you to go backwards and figure out the value a? Right? That's what the inverse function is all about. We want to be able to go backwards. Right? So let me finish this up. We normally start here at an angle. Start at an angle. And we get an output here, which is some decimal number. Right? And here. This is the normal direction that we normally work with a sine function. And every single angle that we input is going to result in exactly one unique decimal output, something between -1 and 1. But now if we want to go in reverse, we want to start off with the b, right? We want to start for the inverse function. We want to start with b, and we want to go backwards and end at a. So that's what the notation sine inverse means. We input the value b into there, and the output would be equal to a. Right? We input b into the inverse function, and the output would be a. Right? It kind of goes backwards in this process. Okay, well, we can already see a problem with that. Because if we want to go backwards, if I tell you this decimal number and I say go backwards and figure out the angle such that sine of that angle gives you that decimal, well, yeah, clearly we could see that if I give you the decimal b, you can trace it back to a. However, the problem is you can also go over here and note that there's another point right there. So there's another angle right there such that sine of that angle also gives you b. And if we go backwards, there's another point there. And then we can find another point over there. There's another angle right there such that sine of that angle equals to b. And we can find another one there. And then if we keep going, you know this is cyclical. So there's really an infinite number of angles out there such that sine of those angles, all of them, equal to this b value. Right? So we can't uniquely identify an angle if we think of the entire sine function. So hopefully you remember how we fix this in trig is that we limit the domain. We restrict the domain for sine inverse to be this little segment right in here. Let me highlight it. It's going to be the segment from there to there. So we limit the graph to be that, which means that we limit the domain of our function to be all the angles between negative pi over 2 to positive pi over 2. So if we restrict ourselves to just this portion of the domain of our sine function, and likewise only restrict ourselves to this little portion of the graph highlighted in yellow, then in that little segment we can go forwards and backwards and have unique answers. So for every unique decimal here between -1 and 1, there will always be one unique angle within the green such that sine of that angle equals to our output value. That's called being 1-to-1. Right? Our restricted domain, within the restricted domain, the sine function becomes a 1-to-1 function, which means that the inverse exists. Okay, so we would write that sine inverse of the y equals the x. Right? Keeping in mind that a y value is here. This is the decimal value. So for a sine function, we input an angle. For a sine inverse function, we input a decimal. Decimal between -1 and 1. And the output is an angle. Okay, just to confuse people, really, we really just have a love affair with x as our domain in algebra. So if we're thinking of this as a function, here's my function input output, just kind of strictly thinking about input output. Input here, we get an output here. Well, we love to have x as our input, so we flip those, right? Just dummy letters, right? It doesn't really matter whether I call it an x or call it a y. So as long as you get to label it whatever you want, we usually like to flip that around and call this the x because it's the variable of the domain, variable of the input of this function, and the output is y. But regardless of how you call it, we still have the same thing. Remember, whether it's an x or an y, it doesn't matter. The input to a sine inverse function is a decimal number. It's got to be some decimal number between -1 and 1. That's what goes into the sine inverse function. And the output, regardless of what letter you decide to call it, is an angle. Right? So this is our output. It's an angle. And in this case, we're restricting it to be an angle between -pi over 2 to +pi over 2. Good. Okay. Same thing over here. This is just some angle between -pi over 2 and +pi over 2. Okay, so now that we've refreshed our memories a little bit, let's find the following. So we want to find, so let's say given that y equals sine inverse of x. Remember, the input to a sine inverse function is a decimal between -1 and 1. So here, x is a member of -1 to 1. And y is the angle, right? We're going backwards. And so y is a member of -pi over 2 to +pi over 2. Good? Okay, so given this, we want to find y prime. Find y prime. Okay, well, before we do that, though, let's reverse this by definition. If y equals to sine inverse of x, then sine of y must be equal to x. Okay, keeping in mind that those are the values of, keeping in mind that x is a value between -1 and 1, and y is a value between -pi over 2 to +pi over 2. Okay, now let's find the derivative of this with respect to x. So we have ddx of sine y equals to ddx of x. The derivative with respect to x of sine of y, well, that's going to be equal to cosine of y. Cosine of y times ddx of the y, which is going to be our y prime. On the right-hand side, the derivative with respect to x of x is just equal to 1. So this is equal to cosine of y, right, outside of the here, let me make sure it's clear that this is outside of that. So it's cosine of y times derivative with respect to x of y. So this is going to be cosine of y separate from times, and then this is our dy dx, or just y prime. That's actually what we're after, equals 1. So now we divide both sides by cosine of y to solve for y prime. So we get that y prime is equal to 1 over cosine of y. We're really close, but now we got to simplify that a little bit. So let me kind of on the side here, recall one of our most useful identities in trig is that sine squared theta plus cosine squared theta equals 1, right? And theta is just a dummy variable. It could be anything. I could write the same thing in sine squared x plus cosine squared x equals 1. So theta is just a dummy variable, but let's just solve for solve for cosine here. So that means that cosine squared theta is 1 minus sine squared theta. And so cosine of theta equals to plus or minus the square root of 1 minus sine squared theta. Right? So this just applies to anything. This is just an identity. But in particular, we want to think about this particular case here. So for us, y is an angle, right? Y is an angle between negative pi over 2 to positive pi over 2. So this is really cosine of y equals to plus or minus the square root of 1 minus sine squared y, right? Theta is just a dummy variable. But also note that for y being a member of negative pi over 2 to positive pi over 2, in that range, cosine of an angle there, cosine of y, is always positive. Cosine of y is always positive. So that means we don't need the negative. We get to ignore the negative, ignore the minus. So it's just positive root 1 minus. Okay, so that is the same thing as cosine of y. So I'm going to take that information and then just simplify it here and say that that must mean that y is equal to 1 over 1 minus sine squared y all over the positive square root of that. And we're almost done. Finally, I noticed that way up here, sine of y, let me put it in green here, right here, we notice that sine of y equals to x, and this is sine of y squared, so I can replace the sine of y with an x. And that is our final form for this. This is y, so sorry, coming back up here, this is y prime, bringing this down, dividing both. So this is y prime equals this. So y prime equals to 1 minus x squared, and then square root of that whole thing, and then 1 over that whole thing. So y prime equals to 1 over the square root of 1 minus x squared. Okay, so that's our derivative. Given y equals to sine inverse of x, we can go through this whole process, use this identity, use implicit differentiation, and we arrive at our derivative. Okay, so this is how your author presents it. d dx, the derivative with respect to x, the sine inverse of x, is equal to 1 over the square root of 1 minus x squared. Okay, so same thing as this. Let's find one more. If you recall tangent, remember tangent functions, just a rough sketch of it looks like this. Right, it comes this way, goes through the origin, and comes that way like this. There are two vertical asymptotes, one there and one over there. So there's vertical asymptotes at positive pi over 2 and one at negative pi over 2. So likewise, if we have an angle x and we find an output y equals to tangent of x, then normally in this direction, the input to the tangent function, we input an angle, and we're going to restrict it to one period of tangent. So again, it's going to be restricted to negative pi over 2 to positive pi over 2. Not inclusive of the endpoints. Like that. And the output in this case is any real number, right? This goes up to infinity. So any real number. Any real number. Okay, but now if we want to find the tangent inverse, we want to go backwards. Then tangent inverse of y must be equal to x. This is our inverse function. Inverse function. So we go backwards. So for example, if there is some x value here, let's call it this guy right here, and it maps up to some value there, y, some xy. Normally we put tangent of x, which is some angle, gives you some y. And if you want to go backwards, you plug in y into the tangent inverse function, and we get back to x. Right? This is all under the assumption that we are only in this period of tangent, because we know we can have other periods, and so we run into the same problems that we had before when we want to go backwards if we don't restrict our domain. Okay, and just like before, we have this other issue where algebra just loves x as our input variable. So remember, x and y are just dummy variables. Regardless of what letter you use, y is a real number, and x is an angle, right? So let me put that in here. The thing you input to a tangent inverse function is a real number, okay? And the output then is going to be an angle that's a member of negative pi over 2 to positive pi over 2. And that remains true no matter what letters you use. So we could put tangent and inverse of alpha equals to beta. Okay, it doesn't matter. This has to be some real number. This has to be some angle between negative pi over 2 to positive pi over 2. Okay, but you know, people love x and y, so instead of using or sticking to the x and the y, we flip it around and say let's let that be the x and that be the y, just because we like to think of this as our input variable to this function. So hopefully that doesn't confuse you too much. Okay, so let's start all over here. So then y equals to tangent inverse of x, right? So given this, we want to find y prime. And just to refresh our memories, just to make sure it's clear, x is any real number. X is a member of anything from negative infinity to positive infinity, any real number. On the other hand, y must be an angle that is between negative pi over 2 to positive pi over 2. Okay, so keep that in mind. All right, so we want to find y prime. So if y is equal to tangent inverse of x, then it must be true that tangent of y is equal to x. Good. So now that we have it like this, we're going to take our derivative. Let's take the derivative with respect to x of tangent y equals the derivative with respect to x of x. And the derivative of tangent y is going to be equal to secant squared y, and then times the chain rule times the derivative with respect to x of the y. On the other side, that's just going to be a 1. The derivative with respect to x of the function x is just 1. And this is what we're looking for, right? dy dx. So this I'm just going to rewrite as y prime. And this is secant squared y times y prime equals to 1. So I'm going to divide both sides by secant squared y and get that y prime equals to 1 over secant squared y. And now I'm going to use an identity to rewrite this as follows. I'm going to rewrite this as y prime equals to 1 over 1 plus tangent squared y. and that means that y squared equals to 1 over 1 plus, now I'm just going to rewrite it this way, tangent of y squared. Tangent squared y and tangent of y squared, same thing. And, well, over here, look, tangent of y equals to x. So let's rewrite that as x. And so we get that y prime equals to 1 over 1 plus x squared. Okay, so that's our derivative. Zoom out and capture the whole thing. Okay. So let me box that up. That's our derivative. And your author presents it this way. The derivative with respect to x of tangent inverse of x equals to 1 over 1 plus x squared. Okay, same thing we got here. Okay, so other common derivatives are these. Okay, so here's another little table that your author provides that organizes all the other inverse trig functions, the derivatives of other inverse trig functions, and they can be derived in a similar way, right? So I worked out sine inverse and tangent inverse, but the others can be worked out in a similar kind of way. Okay, so let's do a couple of examples that use these. Okay, given y equals to 1 over cosine inverse of x squared, find y prime. Find y prime. Okay, so let's find that out. So y prime is going to be equal to taking the derivative with respect to x of this. I'm going to go ahead and rewrite it this way. Cosine inverse of x raised to the negative 2 power, right? And we want to take the derivative of that whole thing. Raised to the negative 2 power just takes care of this 2 right here. Okay, so by the chain rule, this is going to be that y prime equals to negative 2 times cosine inverse of x raised to the power of negative 2 minus 1 times the derivative with respect to x of the inside, right? This is the chain rule. So it would be times cosine inverse of x. Good. So this is going to be y prime equals to negative 2 cosine inverse of x raised to the negative 3 power times the derivative with respect to x of cosine inverse of x, right? So this is the derivative of that whole thing. And as we just saw, we can reference our table. This is going to be equal to a fraction where we have a minus 1 in the numerator, and the denominator is going to be 1 minus x squared. That's the derivative of this. Okay, well, all we have to do is simplify it a little bit, but that's basically our answer. So I'm going to bring this up here and say y prime equals to a giant fraction where in the numerator I'll end up with a negative 2 times a negative 1, which equals to a positive 2. And then in the denominator I'll have both of these two. So it'll be cosine inverse of x times, and then this part, which will be 1 minus x squared inside a root. Okay, and then all of this is raised to the power of 3. Okay, so this is this guy, this is in the denominator, and negative 2 and negative 1 gives you a positive 2. There's our answer. Okay, let's try one more. Okay, given f of x equals to x squared cosecant inverse of x, find f prime of x. Find the derivative. Okay, so that means that f prime of x is going to be equal to the derivative with respect to x of this whole thing, x squared times cosecant inverse of x. This is going to be a product rule, so that means that f prime of x is equal to d dx of x squared times cosecant inverse of x plus x squared times the derivative with respect to x of cosecant inverse of x. Okay, so this derivative is easy. That's f prime of x is then going to be equal to 2x, the power of 1, times cosecant times cosecant inverse of x plus x squared times the derivative of cosecant inverse of x, which we can see by our table that this is equal to, and this derivative is going to be equal to -1, and then x times, and then the square root of x squared plus 1. Okay, so all we have to do is simplify this a little bit, and we're almost there. First of all, I can see that this guy will cancel with that guy, and that's about it. So the derivative with respect to x is going to be equal to 2x cosecant inverse of x minus from there, and then we have a giant fraction where there's still one x surviving in the numerator, and the denominator will have x squared minus 1 square root, square root of the whole thing. Okay, all right, so that's our derivative. Note, however, I just want to point out something. Note that the notation we use to indicate an inverse function is this little -1. So cosecant inverse of x, we write this way. This is the inverse function. Inverse function. This does not equal 1 over cosecant of x, right? So make sure you don't make that mistake. It's a very common mistake here. People want to do that. You can't do that. In algebra, we did use that little -1 to represent that. So in algebra, if we had a -1 like that, that really does equal to 1 over x. But that doesn't equal that here. Now, it's cumbersome notation, but we can have this, the inverse function of x, and then the entire thing to the -1 power, so it's an exponential now. And so now this can be equal to 1 over cosecant inverse of x, right? So in this context, we can do it like this or like this. But here, this is meant to be an inverse function and does not equal to that. Okay, so hopefully you have everything you need to get started on your homework. Please come by my office hours if you have any questions.